Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving a very nice rational equation with complex numbers. We have z to the fifth plus z minus 1 divided by z cubed plus 1 equals 0, and we're going to be solving for z values. Now, why did I give it to you as a rational equation rather than a polynomial? Because if a fraction is 0, then the numerator is 0, right? Yes and no. For example, if you have an equation like this, and this is equal to 0, it doesn't mean just the numerator 0, because that's going to give you x equals plus minus 2. But as you should know, x equals 2 makes this undefined, right? Because you're dividing by 0, or maybe indeterminate, who knows, whatever you call it, doesn't matter. 0 divided by 0, and you can't divide by 0. Okay, so that's problematic. So we have to be very careful. But the million-dollar question is, are there any z values that make the denominator 0 while making the numerator 0? Or at least, making both of them 0 at the same time? That's a good question. And that's what we're going to try to answer first, because that's critical. Okay? So stay tuned, because we're going to be doing lots of fun. First of all, the numerator is quintic, and we don't have a quintic formula. Too bad, right? So we're hoping that it's going to simplify a little bit. So how do we solve a problem like this? If you haven't made up the problem like I did, then solution method may not be immediately available. And I know the general tendency is to use long division or polynomial division, whatever, right? Because you're hoping that this is going to simplify and we're going to get a quadratic from here. That's wishful thinking, but that might work, right? You can give it a try, definitely. And you should. That would be the first thing you try. But since having known what this is gonna get to, because I kind of thought about this problem, so I guess we could call this problem homemade, right? And if you're new to complex numbers, go ahead and check out my lecture videos. I go over basics of complex numbers. Anyways, it's a quick intro, and let's get to work. So I want to start with an assumption, okay? And you might be questioning it, like, why? You'll see. Okay. Suppose z squared minus z plus 1 equals 0. Now, I'm not necessarily talking about the same z. Let's just assume that there is a complex number z for which this is true, okay? And then this implies z squared equals z minus 1. Those of you who are familiar with complex numbers probably already figured it out, but let me tell you the whole story. I'm going to build powers of z, and I always want to get a linear answer like az plus b. Make sense? So to get z cubed, what should you do? Multiply by z. That should give you z squared minus z. But we know that as a formula. This is a formula that we're going to keep using. Z squared is always going to be replaced with z minus 1. If you do that, you're going to get z minus 1 minus z, which is negative 1. And that's just awesome. Let's take note of that. Z cubed is negative 1. Doesn't this mean z is equal to negative 1? No. Because a complex number has 3 cube roots. Negative 1 is one of them, but that's not the one we are interested in. Because in this case, it's not negative 1. You can tell, right? Plug in negative 1, it's not going to work. That's not good, right? It's actually good. So let's go ahead and continue with higher powers. Z to the fourth is just going to be that times z, which is negative z. That's nice. And then z to the fifth, this is where I need to stop, is going to be this times z, which is negative z squared. But z squared is z minus 1, so it's the opposite, negative z plus 1. And that's just awesome. You know why? Because if z squared is z minus 1, or if z squared minus z plus 1 is 0, same thing by the way, then z to the fifth equals negative z plus 1, or z to the fifth equals, actually, never mind. I wanted to write it all together, or z to the fifth plus z minus 1 is equal to 0. So if this is 0, this is 0. What does that mean? Houston, we have a problem. Don't worry, Houston, we have a solution as well. So, does that mean this is divisible by that? That's a good question. Something to think about. But this should look familiar to you. Z squared minus z plus 1. So here's what we're going to do. We're going to factor z to the fifth plus z minus 1 having known that these two polynomials have a common factor. So z squared minus z plus 1 should pop up somewhere, right? Hopefully. Let's find out. So we're going to go ahead and do the following. We're going to add z squared to this and then subtract it and continue with the rest. Now, why did I add z squared? You might be questioning. Because, remember, we have z cubed plus 1 in the denominator, right? And if you take out a z squared, this is z cubed plus 1. In other words, z to the 5th plus z squared is a multiple of z cubed plus 1. But why did I use that? Because whatever follows will be a factor of this. You get the idea? It's kind of complicated, but if you keep doing these things, you'll actually have an eye for these and it'll be easier for you to see these things. Okay, right now it might look like rocket science, and don't worry about it, you'll get to the hang of it. So now this is what I have. Let's go ahead and finish the factoring. This is sum of two cubes, which can be factored, and of course it contains this factor. So now along with the z squared and the rest of it, we can do the following. Z to the 5th plus z minus 1 equals z squared times z plus 1 times z squared minus z plus 1 minus 1 times z squared minus z plus 1. Now, this is my common factor. I'm going to take it out, z squared minus z plus 1. And the second factor is going to come from here, z cubed, I need to distribute, plus z squared minus 1. Awesome. And we want this to be 0, right? Maybe not. Let's go ahead and do this. Plug it in. Remember our expression was z to the 5th plus z minus 1 divided by z cubed plus 1. Now I can replace the numerator with these two factors. And the denominator is sum of two cubes, remember? And we can go ahead and cancel these out and end up with something super duper nice. Now I have a cubic in the numerator. I have no common roots, so we're clear. Are we? Well, whatever makes the denominator 0 is z equals -1, but we know that z equals -1 is not a solution of this, by substitution of course, then we're good. So all we have to do is cross multiply. We know that we need to check z cubed plus z squared minus 1. But don't get me wrong, z equals -1 is not a solution. It's a non-solution for this equation, okay? So all we have to do is solve this cubic. How do we solve it? I'll show you a quick method. Replace z with w minus 1/3, and then when you plug it in, you're going to get w minus 1/3 cubed plus w minus 1/3 squared, and I'll tell you why I use that. Because the idea is you want to get rid of the quadratic term. In order to do that, you look at the coefficient of z squared, negate it, divide by the degree, and then assign a variable to it, and that way you'll get rid of the quadratic term. Because this is going to give you w cubed minus 1/3w equals 25/27. So in other words, this is a depressed cubic. It's under depression. And you can solve it by doing the following. Divide this number by 3. That's going to give you AB, which is -1/9. I'm kind of giving you a shortcut for the cubic formula. And a cubed plus b cubed is going to equal this number. And now you have an equation or system of equations. And w is equal to a plus b. And from here you can solve it. But wait a minute, this is way too much work. Don't worry, I got it for you. Or I mean, Wolfram Alpha did it for you. But I'm just going to share with you what it is. And this is what the graph looks like. Obviously, there's only one real solution, which I'm going to show you. If you use the cubic formula, hopefully you'll end up with something like this. Check your work, take a screenshot. And there are two complex solutions, one of which I'm sharing because the other one is so similar. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.